I'm going to tell you about the modern nuclear model of the atom. Now, you know most of these aspects of what an atom looks like already, I'm sure. But just to review quickly, you probably know that atoms are made up of subatomic, smaller than atom particles called electrons. We'll use the symbol E minus for that, protons and neutrons. The protons and neutrons form a compact central nucleus that contains most of the mass. The electrons, on the other hand, form a thin cloud around that nucleus. We're going to discuss three important experiments that provide evidence for this model. So the first one is a cathode ray experiment. This was done by J.J. Thomson way back in 1903. Here's an almost correct drawing of the model. You can see here we have this glass tube. This is a vacuum tube. On the one hand, we have the negative electrode, which should be called the anode. So that switched, and here's the positive electrode. That should be called the cathode. But in any case, you get the idea. As soon as you turn on the voltage supply, this beam of particles shows up. Moreover, if you have a positive plate up here and a negative plate down here, you see the beam of particles bends towards the positive plate. So, what can Thomson conclude from this? Well, the particles must be negatively charged because they're going away from negative anode and towards positive external plate. So they must be negatively charged. Now, Thomson did one other thing. He swapped out the electrodes for different materials, tried all different kinds of materials for the electrodes, and he found that the particle behavior didn't change. It was independent of the electrode material. So there must be a negatively charged particle that's common to all elements. What could that be? Particle with negative charge common to all elements. Let's call it, yes indeed, this is the discovery of the electron, which is a negatively charged particle common to all the elements. Alright, experiment number 2. This one's a little more complicated. Here, Ernest Rutherford used a gold foil. So here it's like aluminum foil, except it's made of gold. And he shot some radioactive alpha particles at the gold foil. And what he saw is that with this detector screen, he could see that some of the particles bounced back at sharp angles, some were deflected quite a bit, others were deflected not so much and basically made their way through. In fact, if you counted them up, 99.95% of the particles have almost no deflection, so they come through just on this center line. Almost all of them go straight through. It's only 0.05% of the particles that bounce back, and some of them at very sharp angles. Why would that be? What does this reveal about the structure of the gold atoms? Well, it's instructive to realize that, in fact, Rutherford was surprised because before the experiment, Rutherford assumed the atom was like a plum pudding. So here's the plum pudding. You've got all of this red stuff he considered positive pudding. So you've got this positive like jelly-like substance, and then inside that are the negative raisins in the pudding. Now, if that were the case, though, the alpha particles, which are positive, would come through and they just have to ram their way through this positive jelly, and these negative electrons would maybe give them minor deflections up or down, but the net effect would they would all go straight through. There would be no opportunity for them to bounce back. But the alpha particles didn't go through with only minor deflections from the electrons. We know that something else happened. So let's go back to what happened and what the gold atoms must really look like. So what really happened, remember, is that most of the alpha particles went straight through, and then some of them were deflected, and some were bounced back at sharp angles. So it must be that there's a particle that's compact and massive. It's positively charged, so it deflects these positive particles. And it's at the center of the atom. what should we call this? A particle that's compact and massive, positively charged at the center of the atom. What should we call it? This is the discovery of the nucleus. Okay, so we're building our atomic model so far. We have an electron, we have a nucleus, and we know the nucleus is positively charged. Here's another experiment, the mass spectrometer, developed in the 1950s by many different people. It's not just attributed to one person. It's a little complicated. Let me walk you through it. So you start with a chemically pure sample, and you shoot it in here. So this might be just pure neon gas, or it might be pure, you name it, some pure substance, some pure compound or element. It comes in a beam of particles, and then we shoot electrons at it, an electron beam, maybe a cathode ray, and this ionizes the particles. So now they all continue on, but now they're positively charged because they lost one of their electrons. They're accelerated through some electrically charged plates. So now we have a positively charged accelerating particle. Passes through a magnetic field. What the magnetic field does is it puts a force on any accelerating positively charged particle, which is exactly what we have. Now the force is going to be the same for every particle. That's just a little bit of physics you're going to have to trust me on. But even though the particles are experiencing the same force, some of them are deflected a lot, and others are deflected not much at all. Now why would that be, the same force? And some deflected a lot and some not much at all. Well, it must be the ones deflected a lot are light and the ones deflected not much at all are heavy. I mean, after all, you can think about maybe a sports analogy where if the quarterback gets hit, he gets deflected a lot because he's light, whereas if the center gets hit, he gets deflected not much because he's heavy. Okay, what does this mean? Well, you have to think about, why would a chemically pure sample have particles with different masses? Why would that be? There must be a particle that is chemically neutral, doesn't change the chemistry, but still has mass, and it's present in these atoms or compounds in different numbers. So what particle could be neutral, and still have mass? Yes, indeed, this is the discovery of the neutron. So now, what do we have? With these three experiments, we've shown that we've got electrons that are negative. We know that from the cathode ray experiment. They form a thin cloud. We know that from the gold foil experiment, so they don't deflect the alpha particles. And we know we have a nucleus from the gold foil experiment. We know it's positive, massive, and compact. And inside that nucleus, we know there must be neutrons that are chemically neutral, but still have mass, which then just leaves, well, where does the positive charge come from? That must be from the protons. So we have our modern nuclear model that has electrons, neutrons, and protons. That's it for today's video lesson.